As we get ready for our bonding unit, we need to finish up some of these periodic trends that determine how these elements bond together when they do form bonds. And so the big thing we're going to talk about is electronegativity. We're also going to talk about how the electronegativity affects ionization energy and something called electron affinity. But first, for electronegativity, make sure you're on the next blank periodic table in our little half sheet that has those several blank periodic tables on it. I believe this is going to be the fourth one on the back side. So on that back side, label that next blank periodic table, label it electronegativity. Just like this one's labeled electronegativity right above. And so we're going to see, first of all, let's see the definition and talk about what's going on here in this little visual. Let's start with the definition. The definition of electronegativity, and we're continuing in our Cornell notes in our journals. Electronegativity is the strength of an atom to take an electron from another atom. The strength of an atom to take an electron from another atom. That is our definition. And so we do have an example here. We have a table of electronegativity values, and you can see that on the first group here, we start off with hydrogen with a 2.2. Relatively large number if we compare the values going down that group. So this is the strength of an atom to take an electron away from another atom. So hydrogen has the greatest strength to take away electrons within its group. If we look across a period, we'll see that the value gets larger and larger as we move across. That means as we move to the right, these elements get stronger and stronger with being able to pull away electrons from other atoms. So where does that come from? If you remember, the last thing that we talked about was atomic radius. And so here I have a picture of atomic radii. And we'll notice kind of a reverse relationship here, where if you look at the radius of the atoms, remember that they get smaller and smaller as we move to the right because we have stronger proton pull as the atomic number increases. Well, since there is a stronger pull, positive pull from those protons, that is actually what's going to contribute to these pulling electrons from other atoms as well. So not only is the increasing strength of the protons, the increasing nuclear power here, affecting the size of these radii, these atoms, it's also going to affect how strongly these elements can pull electrons from other atoms, not even themselves, but also from other atoms. And so that's what this is showing us here. If you are an element on the left-hand side of the periodic table, you tend to, if we're looking at most of the values here, you tend to not really have that strong of a pull on your electrons. So this little ball here represents electrons. Since these elements here have very strong pulls for electrons, they will be taking the electrons that are being donated from anything that's on the left-hand side. And so that, again, is electronegativity. So the table below shows the relative strength of each atom. Notice the right side of the table tends to have higher numbers than on the left. Also notice that helium, neon, and argon don't have numbers. They are noble gases and are very stable. They don't want to take or give electrons. So they don't really have a value or a strength because they don't play this game here. They don't play the I'm going to give up an electron or I'm going to catch an electron. They are stable in the configurations that they exist at. So their electronegativities we don't measure in the scale that we use for electronegativity. Okay, so what else do we need to write down? We have our definition. We have electronegativity labeled on our blank periodic tables. What else do we need to write down? Following the Cornell note format, we can write down on the left-hand side electronegativity and periodic table trends. On your right-hand side, we can write in an element group, the electronegativity decreases as atomic number increases as a result of increased distance between the valence electron and nucleus. Moving left to right across the periodic table, electronegativity increases. Moving top to bottom down the periodic table, electronegativity decreases. So this is our trend. And if we look, we have another visual. Our atom here. These are protons with a positive pulse magnetic attraction for electrons here. They're going to attract electrons. If we get larger atoms that have many energy levels of electrons, well, those inner levels of electrons act as shields, and so they kind of shield the outer energy level, the valence energy levels, from that positive pull in the electrons. So the more levels, the more shielding there will be from the positive pull of the protons and those free-floating electrons. And so that's contributing to our decrease in electronegativity, moving from top to bottom. So to write and label your electronegativity trend on your blank periodic table, I really like this periodic table here that shows in colored segments the strength of the ionization, or excuse me, the electronegativity. And so I would suggest that this is how you label. You might want to pause the video at this point, grab a colored pencil, any color, and color them in just like it shows here to show the electronegativity. And there are a couple of other things that we can do to label the blank periodic table for electronegativity. Here's our general trend. It increases as we move from left to right, decreases as we move down. But I also want you to see that there's a general trend starting small here and moving towards a greater value here. And so I would suggest that we also add in an arrow that goes in this direction, just to show that this is our strongest. Put that in there, and this is our weakest down here. So pause the video, make sure you annotate that on your blank periodic table. The next thing I want to do is ask you some questions. And we'll go over a question together first. Why is sulfur less electronegative than oxygen? Well, if we look at the different atoms and we look at their sizes and how many valence electrons there are, how many shields there are, sulfur is going to have a lot more protons than oxygen will. So it would have a stronger positive pull than oxygen if we were just looking at nuclear charge. But then notice how many energy levels sulfur has. It has 2 layers of shielding these valence electrons on the third energy level from that positive pull. Oxygen really only has 1 shielding layer, and there's only 2 electrons in that one. The valence electrons are much closer to that positive pull. So oxygen will have the stronger electronegativity because its positive pull in the nucleus from the protons is going to be stronger than sulfur's because sulfur has that shielding involved. Now for questions for you to answer on your own. I'm going to give you 2 pairs of atoms, and you tell me which one has the greater electronegativity and why. So in your journals, we have these 2 examples that we need to explain. Which has the greater electronegativity between sodium and chlorine? And then tell me which has the greater electronegativity between sodium and calcium. And in both cases, explain your answer in terms of atomic radius and atomic number. So don't forget to include that in your explanation. Go ahead and pause the video, put that into your journal on the right side of your Cornell notes, and then when you're ready, move on to the next step. Electronegativity plays a very big role in how atoms combine with each other. So electronegativity, even though we may not specifically say this word over and over again in the next unit, it is going to play a very important part. So remember that in electronegativity, it increases as we move to the right, which means that across a period, the atoms will get smaller and smaller and smaller as that power of the protons increases, which means these elements here, they do not want to let go of electrons. They want to gain electrons. And so on our last periodic table that is blank, on our periodic tables sheet, let's go ahead and copy this down and make sure that you label, let me make it a little bigger, make sure that you label the metals and the nonmetals because that is important to how these elements are going to be bonding. So a metal gives electrons to a nonmetal. Metals will give electrons to nonmetals. The metal becomes positively charged and the nonmetal becomes negatively charged. Now they attract each other because opposites attract. There are special names that we use for these negative and positive ions. A positive ion is a cation. And I remember that because it has a T in it, which kind of looks like a plus sign, so that's positive. The negative ions are anions. Anions. And I remember that through alliteration. The letter N's repeat themselves. Negative. And anion is negative. Okay, so we'll talk about the formation of these charges when we do the activity in class for ion formation. But this general trend, pause the video if you need to, write this down, and label these one color onto the left of the stair step, label these to the right of the stair step, metals and nonmetals. Okay, so now that we have that, let's look at these different trends that form. So we have ionization energy. And ionization energy is the amount of energy required to remove an electron. So again, it's going to increase as we move to the right because these elements up here don't want to get rid of their electrons. They are greedy. They actually want more electrons. Something that's down here is going to have a very small ionization energy because their power of the protons has so much shielding done by those other electron energy levels. So pause the video if you need to write that down. Here's a general equation we can use. Neutral atom, put some energy into it, and then we're able to pull that electron away, which leaves a cation. Okay, next. Electron affinity. Electron affinity is basically just the opposite of ionization energy. Where ionization energy is energy required to pull away an electron, electron affinity, because this is what the atom wants to do, energy is released when the electron is added. And so these two periodic tables are broken down. You'll notice they're missing the middle part, kind of like that last blank periodic table that you have. So on those blank periodic tables, go ahead and label electron affinity increasing, going up a group, going across, going up a group, going across for ionization energy also. So label those two things. Make sure you have these definitions. And we'll continue with the bonding unit in the next series of videos.